If you haven't already, please get out something to take some notes on. There is one last thing about extracting information from the periodic table that we did not cover yesterday in the notes, and that is electron configurations. This is the arrangement of the electrons around the atom. And so that is the definition of an electron configuration. It is the arrangement of the electrons around the nucleus of the atom. And this goes back, while you're jotting this down, to Bohr's model of the atom. In Bohr's model, remember, it has the nickname the planetary model, and the electrons exist on specific rings or orbitals. In the lab the other day, where we looked at the bright line emission spectra of these elements, we saw that elements jumped from one orbital to another and then fell back down as well. And that is where these electrons are on those orbitals. But it turns out it's different than Rutherford's model, where the electrons could just be anywhere around the nucleus as long as they are orbiting it. Bohr said they had to be on specific orbitals, and it turns out that there's certain patterns there that we're going to follow. It turns out that each orbital can only hold a limited number of electrons. Now, we're not going to get too complicated with the electron configurations. We're going to keep it basic in here. Always like to show you what you have to look forward to in chemistry, though. And so it turns out that the most complicated electron configuration you're going to do this year is calcium. The chemistry way of writing calcium is this. And you don't need to copy this down. Normally we do this all in one line, but I ran out of space, so I'm going to move down to the next line. That's calcium, although we sometimes abbreviate it this way. Or you can abbreviate it this way. Or we get into doing what's called quantum numbers. And quantum numbers look something like this. And that there only takes care of that first arrow, or one of those two there, or something that's buried inside of there. You end up with 20 sets of 4 digits inside of parentheses like that. Fortunately, you don't have to do anything that complicated. So before you freak out and start groaning, the electron configuration that you're going to do for calcium is this. If you want to jot that down as an example for calcium, great, go for it. But you will do this one later in the year, and that is the most complicated it will get. The reason why we stop there is because things get weird on the periodic table once we get into what I call the indented section, that section in the middle, starting with atomic number 21, scandium. And so because of that, we won't get into more complicated electron configurations. So the electron configuration of calcium is there. Anyway, as I said, each orbital can only hold a limited number of electrons. By the way, the asterisk there is for a footnote that comes up here in just a moment. But there are some synonyms that we use in place of orbital, because orbital is technically a chemistry term, and since we are simplifying down the chemistry terms, there are some synonyms that can also be used there. So that footnote will come up here in a moment. But anyway, the first orbital can hold 2 electrons total, or 1 pair of electrons is how we'll tend to refer to them. The second orbital can hold 8 electrons, or 4 pairs. The third orbital can hold 8 electrons as well, or 4 pairs. And the fourth orbital can hold 18 electrons, or 9 pairs. Although we will only go as high as 2 in class. We will never put 18 into there, and it actually turns out before you can fill up to 18, it turns out that this one here gets 8, then we put 2 here, then we start putting more in here, and we'll add 10 more for a total of 18, then we start adding into here, and like I said, things get crazy on the upper parts of the periodic table, so we'll never actually go that high. Now, what we actually mean by this is the first orbital, I'll draw over here in black, and that's around the nucleus. Keep in mind, this is just a model, it's not the scale, but the nucleus would be in the center there somewhere. And so that orbital can hold on it 2 electrons. It's the first orbital because it's the first ring from the center. We order the rings from the center. The next orbital can hold 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. You may wonder why I went around and did it like that. Trust me for now, we'll explain it in more detail later on when we actually get to bonding. What I will say is start in one position and we kind of go above the side, below the side. I normally go clockwise around and start at the top. You could start at the bottom and go counterclockwise around. It doesn't matter as long as you're consistent. The biggest thing is if this orbital doesn't actually have 8 electrons in it, let's say it only had 6, this would be incorrect. Instead, what is proper for 6 is this, and I'm going to redraw it here, so for those of you who are still copying it down who missed it, okay. 1, 2, 3, 4, 5, 6. Where there are 2, there's emphasize lonely electrons. Now again, this ring can hold a maximum of 8, so resetting that there, there's 8. The next ring out can also hold 8. 1, 2, 3, 4, 5, 6, 7, 8. And the next ring out can hold 18, but the most we're ever going to put into it is 2. So rather than drawing all 18 here, what I'm going to do is I'm going to label it as the rest. There's only 2 elements that we'll put out there, and so that's that. It turns out that the lower orbital must be full before the next orbital is used. And I'll make this make sense when we start doing some examples, but before we start doing those examples, you will want to get this diagram copied down. If you're not done, I would say just go ahead and pause the video. Otherwise, I'm going to move on here. Oh, apparently I don't have the subnet there. So, if you want to jot down all the different things that we can, sometimes we'll refer to them as rings. I think I've already done that. Orbital is another term, shell is another term, and energy level is the other term. All of those are used somewhat interchangeably here in a general science class setting, a physical science class setting. If you take chemistry specifically, each one of these energy level, shell, orbital, all mean specific things. And so then we will deal with those as they come. Anyway, I'm going to move into doing some examples. You, of course, still have your notes in front of you, but they won't be here on the screen to refer to. But let's just start with the electron configuration of hydrogen. Hydrogen, you need to look up its atomic number first. And when you look up the atomic number on the periodic table, you will find that it normally has, or it has an atomic number of 1. That means that it has 1 proton, always, and that it usually has 1 electron. So if we drew that as a orbital diagram, 1 ring, electron. It turns out that in reality, there are the other orbitals there. They are just empty. And if you would like to draw in empty orbitals around it, feel free to. It is not at all necessary. In fact, I discourage you from doing it. Now, that is the diagram way of doing it. So this would be a orbital diagram, electron configuration, or EC. This is the numeric electron configuration. The numeric electron configuration is 1. Just tells us the address of that electron, that there is 1 electron in that orbital. Next, we do helium. Helium, you need to look up its atomic number on the periodic table. If you don't have your periodic table out already, you of course should have it. You're going to need it for the homework that you're getting today. Anyway, helium has an atomic number of 2. That means that it has 2 protons always, and that it normally has 2 electrons. So for helium, we're going to do an orbital diagram as well. That's 2 electrons. 1, 2. Since that energy level can only hold 2, we usually put them across from one another. That's because the electrons have the negative charge, and they would repel one another, and so they want to be as far apart from one another as possible, and the furthest apart they can be on that energy level is to be on opposite sides of it. As the numeric version, its electron configuration is 2. Piece of cake so far, right? Alrighty, so now we're going to move into lithium, next element on the periodic table. If it's the next element, then obviously its atomic number is going to be 3, which means it has 3 protons, and it means that it normally has 3 electrons. So here things are going to get a little different. We put the first 2 electrons on the lowest energy level. But now that energy level is filled up. It can only hold 2 electrons, or 1 pair of electrons. It's filled up. We have to go out to the next energy level. And that next energy level has 1. Its electron configuration, though, is not 3. Instead, we want to list out the addresses of the electrons. So on the first energy level, there's 2. On the next energy level, there's 1. And to separate them so it doesn't get confused with 21, we use hyphens or dashes. It is not a minus sign in this case. It's simply a hyphen or a dash to separate the numbers. With lithium out of the way, we're going to stop going in order. We're going to jump forward to a atom like oxygen. Oxygen has an atomic number of, give you a moment to look it up, 8, which means it has 8 protons and normally has 8 electrons. The first 2 electrons are on the first energy level. The next electrons are on the second energy level. So we've already done 2, so there's 3, 4, 5, 6, 7, 8. And if we look at this then, 2 electrons on the first energy level, and 1, 2, 3, 4, 5, 6 on the second energy level. So 2-6 for that one. We'll do one final example here, and that is calcium. Like I said, this is the toughest one you're going to do all year. All the others are somewhere in between these examples. So calcium, I'll give you a moment to look up its atomic number. But it has an atomic number of 20. That means it normally has 20 protons. And, excuse me, always has 20 protons and normally has 20 electrons. So first energy level can hold how many electrons? 2, just like before. 1, 2. Next energy level can hold, we didn't fill it up there with oxygen, can hold 8, which means we're going to go 3, 4, 5, 6, 7, 8, 9, 10. That's 10 electrons total that we've placed. 8 on that second ring. That second ring is filled up, so now we need to go out to the next ring, third ring, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, or just to emphasize here real quick, that would have been 11, 12, 13, 14, 15, 16, 17, 18. So we've used up 18. We're still not quite to our 20. We have 2 more to find a home for. So we draw the next ring out here. And remember, this third ring can hold more than 8, but it normally holds 8 first. Then it pulls, the next ring gets some before it fills up. And we're not going to get into that crazy chaos. So we have 2 electrons left to place, and the rest of them go out here on this 4th ring. That gives us a electron configuration in the number form of 2 hyphen 8 hyphen 8 hyphen 2. 2 8 8 2. That's for electron configurations. Examples, you'll do more of these. In fact, you're going to do all of the ones between hydrogen and calcium on the homework assignment today. Lastly, we have valence electrons, and valence electrons is the number of electrons on the outermost energy level. It does not matter what the last energy level is, but the last energy level to be used. And it is always the last number in the electron configuration. I'm sure some of you are still writing, so I'm going to go for a split screen here so that the valence electrons stay over there, but I'm going to come back over here onto the electron configurations and highlight the valence electrons. So on hydrogen, there is 1 valence electron. On helium, there is 2 valence electrons. On lithium, there is only 1 valence electron. It's the outermost energy level, how many ever electrons it has. That means oxygen here has 6, and calcium has 2. To give you a little bit of preview for the periodic table, the next topic that we'll be covering, notice hydrogen is above lithium on the periodic table, and notice they have a different number of electrons total, but they have the same number of valence electrons. That's important. But the number of valence electrons is the last number on the energy level. In fact, what will happen later in the year, and I'm going to draw this over here underneath of this slide, I think, but later in the year, we'll get to where we take oxygen here, and we won't draw the inner electrons, and we won't even draw the ring, and we'll get to where we're drawing just the valence electrons. And normally what we'll do in that situation, so that there's something there, is we will put the element's symbol inside there. In this case, it'd be an O, which I didn't want you to get confused with the ring, so I didn't start out by drawing that. But we will get to where we are just drawing valence electrons. And valence electrons is what chemistry is all about. The atom's mass mostly comes from the nucleus. Over 99% of the mass of the nucleus. Over 95%, 99% of the space of the atom is the electron clouds, but only the outermost layer of the electron clouds is actually what matters when it comes to chemistry and chemical reactions, why atoms behave the way they do, why they bond to some things, why they react with something. It all comes down to just those outermost electrons. Chemistry is all about these valence electrons. And in fact, what happens is atoms tend to want to fill up their outermost energy level. They like to have a full outer shell, and they can do this by gaining or losing electrons. And that is called the octet rule. It's called the octet rule because, generally speaking, rings hold a maximum of 8 electrons. Again, there are exceptions. I've mentioned it already. But the oct in octet comes from 8. The octanoctopus, 8 arms. The octanoctagon, 8 sides. The octanoctober. Actually, it used to be the 8th month of the year, I believe. Is where its name came from. No, I lie. It came from a Roman emperor. Now that I think about it. Anyway, but the oct here means 8, and it's because atoms generally want 8 valence electrons. The main exception is hydrogen and helium. We only want 2 valence electrons. Helium is already there, so it's happy. Hydrogen's not happy because it doesn't have to. It wants one more, or it can get rid of both the ones it has. Anyway, it turns out that metals tend to lose and non-metals tend to gain electrons. Now, at this point, I would normally ask you, what is the charge of an electron? And hopefully you remember, because we just wrote it over here on the left-hand side of the screen in green, that electrons have a negative charge. So if I gain electrons, I'm going to be gaining more negative charge, and gaining electrons results in a negative charge. On the other hand, if I lose electrons, I'm getting rid of negative charge. I'm going to be left with more protons than neutrons, so losing is going to give me a positive charge. And so metals tend to become positive, and non-metals tend to become negative. And charged atoms are called ions, whether they are positively or negatively charged. Charged atoms, due to gain or loss of electrons. Anyway, that finishes the notes. You will want to keep them handy for the worksheet, but I'm going to go through some example problems on the worksheet as soon as I have it open here. So, if not already, the worksheet needs to be handed out before we go over examples here, and you're going to follow along with the examples on the worksheet. So what I'm going to do is I'm going to read across the worksheet, and I'm going to describe where you find this stuff, and then you're going to finish filling it out. Now, I know, because we normally read left to right, that you're going to want to fill it out by rows, and I'll be honest, it's much easier if you fill it out by columns, if you go up and down. Start at the top of the column, go down, and then go down, and repeat over and over again. So, for starters, mass, and you're going to round it to the nearest whole number, but mass you're going to look up on the periodic table. And so, you may want to make a note of that. That mass is found on the periodic table. I would make that in the margin of above the mass. They are kind of squeezed in around the directions. For hydrogen, when you look it up, its mass is 1. For helium, when you look it up, its mass is 4. The rest I'll let you look up on your own. But I'm going to move on here. Atomic number, you look up on the periodic table. The atomic number is super simple. Hydrogen is 1, and helium is 1. Or excuse me, it's 2, not 1. So, I knew that. Number of protons is equal to the atomic number. So that's simple. Number of electrons is equal to the atomic number. Number of neutrons is not. Number of neutrons, recall from yesterday, is a calculation you needed to do. The mass is protons plus neutrons, so if we run that in reverse, neutrons is mass minus protons. Mass minus protons. So, for hydrogen, it's going to be mass, 1, minus protons, 1. Number of neutrons is 0. For helium, it's mass, 4, minus number of protons, 2, and is 2. By coincidence, this 2, number of neutrons, happens to match number of electrons, protons, and the atomic number. It's not always equal. That, as you can see, with hydrogen. The electron configurations, we just did these two as examples a moment ago, so I'm just going to jot them down here, 1 and 2. We also did lithium just a moment ago, 2-1. Oxygen was 2-6. And calcium way down here was 2-8-8-2. Number of valence electrons is the last number in the electron configuration. For hydrogen, it's 1. For helium, it's 2. For lithium, it's 1. For oxygen, it's 6. And for calcium here, it's 2. The element type, you're going to abbreviate it as a metal or a non-metal. And if you look at your purple periodic tables, on the right-hand side, it's kind of faded, but on the right-hand side, there is a stair-steppy line. Everything to the left of that stair-steppy line, and I'm going to drop that down here next to the metal, everything to the left is a metal. Everything to the right of that stair-steppy line is a non-metal. That should be an R for right. Everything to the left of the stair-steppy line is a non-metal. Everything to the right is a metal. Based off of whether it's a metal or non-metal, it's going to gain or lose electrons. So you'll have to refer back to your notes, but metals tend to lose and non-metals tend to gain. If it's losing electrons, it's going to lose all of the valence electrons. If it's gaining electrons, it's going to gain the number it needs to fill up that energy level. For helium, there's 2 there. That energy level can only hold 2, so it needs to gain 0. Which is part of why we did oxygen as an example as well. I know I skipped the middle section here, but it turns out that oxygen is a non-metal, and it has 6 valence electrons. That energy level can hold a total of 8, which means it needs to gain 2 more to get there. That would result in these things having a charge. If it loses electrons, its charge is going to be positive, and it's going to have a positive 1 charge. There is no difference between a positive and negative 0, so that one's just going to be 0. Oxygen here, though, which lost electrons, is going to lose, which gained electrons. Oxygen gained electrons. It's going to lose, or gain, I keep saying the wrong word there, I apologize. It's going to gain 2 electrons, and gaining electrons is going to end up with a negative charge. So I have a 2 minus charge there. And you're going to repeat that all the way down this column. So just to refresh you again here, the charge will be whether it gained or lost. Gained or lost will result in it being positive or negative, and we just jotted that down in the notes a moment ago here. And then this number that goes with the charge will be the number it gained or lost. So essentially, you're taking this column and combining them into one term here, a positive or negative number. And yes, 1 plus is the same as 1, but we'll take the time to write 1 plus. Also, plus 1 and 1 plus are the same thing. Chemists tend to do number then sign. We do it backwards from how mathematicians do it. I don't know why. I will not penalize you if you do plus 1 instead of 1 plus, but I will always go the chemist way of writing this in chemistry. Anyway, again, I recommend going down the columns on this one, but you need to fill out this, and then take a stab at the oxidation number down at the bottom. Oxidation number is a fancy word for charge. So see if you can find the pattern that exists for charge. If you can't, it's okay. We'll review that later. The biggest thing I'll be looking for is that the chart is completed. The last thing, on the back side, you need to do orbital diagrams of all 20 electron configurations. Make sure you label each orbital diagram. Orbital diagrams are these diagrams that we did here with those. Plan out what you're going to do and make sure you label which one is which element. You need to do 20 of these, and they get bigger as you go along. Plan carefully, please. Anyway, you can have the class assignment that remains to start working on this assignment. And it will be due on Monday.